Hey there, folks, and welcome to another edition of the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey. Today we'll be exploring volcanoes, episode 11. Super excited to do this with you. Geology 101, this video series is set up for those who maybe have had a geology class long ago, or maybe have never had any formal education or training in geology, but just want to learn. It's recommended that you follow the video series consecutively in order. That way you probably have the best context and understanding of what we're doing because we're kind of building up our knowledge foundation as we go. This course is designed completely off of the Geology 101 course I teach here at the college. So it's the same topics, curriculum. You're getting the full meal deal here. The one thing we don't have, of course, are the labs and the field trips, but you can supplement those to some degree with some of my other videos that are here on the channel. So let's just get right to it. We'll probably do several different other episodes coming up to cover this topic. Today we want to just look at sort of an introduction to volcanoes. In future episodes we'll look at the different types of volcanoes, eruption styles, volcanic hazards, and even some ways that we monitor volcanoes in the modern world. So you can see just, volcanoes just captivate the imagination, just their size, their scale, their symmetry or lack thereof. Sometimes we think of volcanoes as things sticking up out of the ground like a big mountain. Other times, some of the most explosive volcanoes tend to be depressions, things that are actually negative relief features or below the horizon, like we have down here at the bottom with Crater Lake. So just some fun eye candy here as we get started with volcanoes. And of course, volcanoes are the manifestation of magma making its way to the surface where it erupts as lava. Now that lava can either stay molten, like you can see in that top left photo there, or that lava can actually be expelled with such ferocity and explosive power that it actually fragments into tiny, tiny shards that we call ash. And then in that range, there's also larger particles that can be erupted as well. And so we're going to explore the array of volcanoes on planet Earth because there's just so much diversity, and recognize probably with the next episode as we get into the different types of volcanoes, the classification system we employ for volcanoes, that just like any classification system, it's not perfect. Mother Nature doesn't care that we categorize volcanoes. And of course, there's lots of hybrids. There's lots of complex forms of volcanoes that don't fit well in the system, the arbitrary system that we've concocted. And so that's worth pointing out and noting. Also realize that this is a Geology 101 lecture series. We're not going to get super deep in the weeds with some of the other types of volcanoes that exist out there. We're just starting with the basics, a good place to begin. So when we think about volcanoes, we might think first about where are they? Where are the volcanoes on planet Earth located? And this map is as good as any other that just shows the location of many of the Earth's volcanoes, ones that are active, meaning active, they're continuously erupting on human timescales, or they at least show signs that they've erupted fairly recently in the past and potentially have the ability to erupt into the future. Geologists tend to classify and label active volcanoes as ones that have erupted in the last 10 or 11,000 years, or ones that actually have the potential ability to erupt sometime in the future. They have an active magma system that sits beneath them. So as you look at this diagram and this map of active volcanoes around the globe, you can see that it closely mirrors our plate boundaries. And I don't have a plate boundary map on here, but think about those plate boundaries we looked at in prior episodes, the ones that rim the Pacific Ocean, the Ring of Fire, as it's commonly called. The chain of volcanoes here in Indonesia closely mirrors the subduction zone, a plate boundary that sits here. And then a couple episodes ago with igneous rocks, we looked at some of the processes where magma gets generated, and we tied those into plate tectonic settings. So we dominantly see these volcanoes forming where we have subduction zones, divergent boundaries, or hotspots. Those are the three dominant tectonic settings where volcanoes tend to be manifested. That being said, there are a few anomalies here and there. There's some volcanoes that don't quite fit that mold, but by and large, we can explain most volcanoes with the context of plate tectonics and hotspots pretty nicely. So they do tend to occur mainly in these locations. So when we look at volcanic eruptions, there's a whole spectrum in terms of how volcanoes erupt. And we tend to use these two terms as end members, effusive versus explosive. Effusive meaning a more passive, gentle outpouring of mainly lava. So you can see in this bottom photo here, we've got a person just sitting there, maybe making a sketch, maybe taking field notes, maybe eating a sandwich for all I know. And they're literally 100 meters or yards or so from an active vent, a volcanic vent at the surface. And yet, knowing what I know about volcanoes, that looks like a perfectly safe location for the most part, unless conditions change. That looks like a sustainable situation. I'm guessing with some degree of certainty that this person walked away from this exact moment in time and lived and survived. So these are our effusive eruptions, the ones like we've seen recently in Iceland, in Hawaii in the past few years. Doesn't mean that they're not hazardous and they don't impact humanity in some negative way, but that their eruptive style is what we call effusive. It's just lava coming to the surface, non-explosively for the most part. And you could actually be quite close to these types of eruptions. At the other end of the spectrum, we have the scene here in the top right, which is from Pompeii. Many of you might recognize that, the 79 AD eruption of Mount Vesuvius in Italy, which was an explosive eruption. And that eruption took the lava that was in the magma or from that volcano, and it erupted it with such force, such explosive power that it shredded that magma into tiny bits of ash. The force of the eruption was so powerful that it sent a barreling cloud of hot ash down the mountain. And that's what ultimately and tragically killed so many people and animals in some of the villages and towns that existed around Mount Vesuvius there many centuries ago. So you can see that, on one end we have volcanoes that maybe we want to go to. Like if you tell me certain volcanoes are erupting, I'd like to buy a ticket and get there as quickly as I can. Like when Iceland erupted in 2022, I bought a ticket the day it started and I was there within a week, and I enjoyed that eruption. I got to be right up close with the lava, take a sample, and walked away just fine. And then there's other volcanoes that exist where if it's erupting, you wouldn't want to be anywhere within, maybe hundreds of miles or kilometers, perhaps, maybe even larger, depending on what it is. So fundamentally, we're going to look at what causes this difference, why we have such a diversity of behavior with these volcanoes when they do erupt. And this is a great summary. This is a great diagram to start with. So let's work through this and make sure we understand this, because this really does explain so much about why we have different types of volcanoes and different types of eruptions. So let's work through this. Let's talk about the rows first, and then we'll work through it column by column. So 3 different rows here. These correspond to our 3 different general types of magma compositions, what we talked about in prior episodes when we looked at igneous rocks. So basaltic or mafic magma, intermediate or what we might call andesitic magma, and then rhyolitic or felsic magma. Realizing that magmas don't come in just 3 flavors. There's hybrid ones that fit in between these two. There's ultramafic magmas. There's a lot of other variables here, but this is a good place to start at this level. Just 3 common general types of magmas. Okay, and then we can look at their chemistries here if we want to. So let's go column by column now. So this is our composition of magma. So we know that magmas vary. So right away we should expect there to be different types of volcanoes, because not all magmas are the same. Some volcanoes are fed by mafic magmas. Some volcanoes are fed mainly by felsic magmas. And so we get different types of eruptive behaviors. Our second column here is silica content, how much silica the magma contains. And this is really one of the most controlling factors in how a volcano will manifest itself. In fact, you can really take this column and it to some degree control some of these subsequent columns we see to the right of it. So this is a huge control of how the magma body and the ensuing volcano will behave. So basaltic magmas, by definition, have very low amounts of silica, around 50% or so. And these percentages matter a great deal. And at the other end of the spectrum, a felsic magma or rhyolitic magma tends to have quite a bit more silica. Think of silica as, well, we'll get to it. We'll talk about viscosity and stuff here in a second. So this one has the least amount. Consequently, the gas content of the magma also is a function a bit of the silica content and the viscosity, which we're going to get to here in a second. So basaltic magmas with low silica content. In fact, I'm going to jump over to viscosity now because I think you can't really tackle gas until you do viscosity. So let's jump over to the viscosity column. Viscosity is how fluid or how sticky and pasty the magma is. So basaltic magmas tend to be the most fluid. They're runny. They don't tend to trap gases as easily. They are the more fluid type of magma. That's what you see in Hawaii and Iceland most of the time. At the opposite end of the spectrum, your felsic magmas tend to be sticky and pasty. They don't flow well. They're sluggish. They're stiff. And so the viscosity is a function of the silica content. Greater silica content equals greater viscosity. And the viscosity also controls the gas content, because if that magma is very sticky and pasty, like a rhyolitic or felsic magma, it's going to tend to trap a lot of the gases. The gases are going to have a hard time escaping from that sticky, pasty magma body. And so those gases, which cannot escape as easily, are going to tend to accumulate. Whereas in a basaltic or mafic magma body, which has low viscosity, it's quite fluid and runny, at least in the world of magmas, a lot of those gases are going to escape pretty easily. And so it's going to have a much lower gas content. If we go to eruptive temperature, the silica content determines to some degree the temperature, and the temperature and the viscosity are somewhat related. So just like honey, we know that when honey is, been in the cupboard for a long time, or maybe you go camping and it's at a low temperature, that means that the honey is very sticky. It doesn't flow well. It has high viscosity. Same with magma bodies. Lower temperatures and higher viscosities go together. At the other end of the spectrum, a magma that has low viscosity, a basaltic or mafic magma, is going to tend to erupt at a higher temperature. So those lavas we see in Iceland and Hawaii are erupting at a much higher temperature than some of the stiff magmas, maybe at like Mount St. Helens or something like that. These last two, second to last column here on the right, tendency to form pyroclastics. Really just think of this column as explosivity, okay? And in a basaltic magma body, because we're not trapping a lot of gas, it's not going to be very explosive. It's going to be very low on the explosivity scale. And in contrast, a rhyolitic or felsic magma, because it's trapping so much of the gas, because the viscosity is so high and it's sticky and pasty and sluggish, that's going to mean that those gases build, the pressure builds, and then finally when we do have an eruption, it's going to be highly explosive. And so if you can make heads or tails of this and kind of work your way through it, this really does explain a lot about volcanic behavior as it relates to different magma bodies. It's also helpful because if you go back to your rock types and you can, let's say, identify you have a rock that you think is mafic, or in this case like a basalt, you have a pretty good idea of what its history was in terms of how it erupted, right? It was non-explosive, came from a mafic magma body, probably erupted as lava potentially, not always, but it might have. And, and then you go the opposite end of the spectrum. So you might be able to come up with a viable story or interpretation of that rock. The intermediate magmas, I kind of like to think of these as bipolar. I mean, I know it just says intermediate across the board. These volcanoes are going to tend to illustrate behaviors similar to either mafic or felsic magmas. They're going to sometimes behave explosively, sometimes not. And again, that's why I like to call these the bipolar volcanoes. They tend to erupt at both ends of the spectrum off and on a bit. Okay, so hopefully this is helpful. Let's look a bit at some of the parts of a volcano. This is just a generic diagram, but as we get into volcanoes, it's important to know that there's different locations and terms we use. So let's go through a couple of these. We don't have to go through all of them. The place where the volcano is erupting, where the lava or ash is coming out of the earth, is what we call the vent. So that's where the action's taking place. That's where the conduit from the magma storage zone or the reservoir meets the Earth's surface. So that's where the eruption is taking place. That might happen at the summit of a volcano, or it could also happen along the flank or the outside margin of the volcano. You might get something like a parasitic cone or a parasitic vent on the side or the flank of the volcano. This is very cartoonish and generic, but in this particular case, this volcano is made out of some layers of lava and some others layers of ash. We've talked about dikes and sills before, I believe. If not, a dike is um, a narrow pathway of magma that cuts across the layers of rock. So you can see the layers going this way along the margin of the volcano and the dike cutting across those layers. Whereas a sill is an intrusion of magma that's parallel to the layers. So notice that the sill and this layer of lava here are parallel to each other. So just some simple names, not too technical there. You probably could have figured out most of those, but just giving you some context on volcano types. Let's wrap up our introduction to volcanoes by talking a bit about exactly what volcanoes produce when they erupt, what comes out of a volcano, and then we'll tie this into hazards later when we look at hazards. So the first thing you think of when you talk about what erupts from a volcano is you often think about lava. Lava as a hazard we're going to see for humans is very low because lava is usually pretty predictable. It's going to follow the topography. It can be modeled if there's an eruption. Geologists and forecasters can get ahead of that and model the topography and figure out where that lava might go. Now, there's other factors that can come into play here that can influence the path of a lava flow, but by and large, it's going to follow the topography. If we have homes or structures in the path of that lava flow, then that obviously presents a huge problem because you can't move those structures. But getting people out of the way shouldn't be too much of a problem. So this is what happens with some volcanoes. They erupt primarily lava on the surface. But as we increase to more explosive types of volcanoes, we have material that's thrown into the air. This is what we call Tefra, or we could call this pyroclastic material. Anything that's shot out of a vent and is airborne is technically Tefra. And it could be a blob of lava. So a piece of lava could fly out of a vent airborne, fall back down to the ground still as lava, and feed a lava flow. But anything that's airborne we consider to be this material here, Tefra or pyroclastic material. And we categorize this material by size. I'll show you a few samples here in a second, but let me go through the different sizes and their definitions here. So the smallest size is ash, generally 2 millimeters in size. Because the ash is very fine, it can be distributed over a very large area. We have in some eruptions around the world, the ash can fall hundreds or thousands of miles or kilometers away from the actual vent. Sometimes we can even detect ash, halfway around the world from a volcanic eruption that took place. It can be carried by the jet stream and atmospheric winds and then fall and be distributed in other places. This is actually a high magnification view of some volcanic ash, and you can see it looks a lot like a rock we'll get to later called pumice. It has lots of holes in it. It's usually made out of volcanic glass, so it's really kind of like pumice in the sense that it's made out of volcanic glass, but it has all these little bubbles in it kind of stretched out. It's nasty stuff to inhale. It's bad in infrastructure on power lines. We'll get to it in terms of a hazard, but ash, that's the smallest size of Tefra. As we move up in size to a little bit bigger, let's say, BB size to maybe, I don't know, golf ball size or so, this would be something we call lapilli. It's an Italian word. And so this would be a little bit bigger. Obviously, if it's a little bit bigger, it's going to be closer to the vent. It's harder to get these larger size particles further away from the vent. It takes more explosive energy. And we sometimes call lapilli that is made out of basalt and has little holes in it. We already used this term in the igneous rock. Vesicular, the vesicles, the gas bubbles. If it's basaltic and vesicular, we sometimes call that type of lapilli cinders, and we even have a type of volcano we'll discuss called cinder cones. And then at the high end of the spectrum, at the largest end, are blocks and bombs. So these would be anything, bigger than, I guess, like a racquetball or something like that. And these would dominantly fall close to the vent. And we do differentiate these a little bit based on their shapes. So if the volcanic eruption is just throwing out an existing rock that's down there and it's just being spat out onto the ground, an angular chunk of already solidified existing rock, that would be what we call a block. If it's actually, though, lava that's being ejected, airborne, and it's molten when it gets thrown out of the volcanic vent. These are what we call bombs, and these tend to actually cool in the air, partially at least, before they hit the ground. They tend to be a little smoother in terms of their shape. So let me show you real quick a few. Let's switch over to the document camera, and I'll show you here just some examples of these. So here is a little vial of ash. So you can kind of see the grain size here and the particles. So just very fine. This feels just a tiny bit gritty, but almost flour-like in its consistency. Nasty stuff, but this is sort of the size that we're talking about when we talk about ash. Lapilli, the lapillis I have here are actually cinders. So you can see these little chunks here of black or dark basalt with little bubbles, vesicles in them. Let's see if I can. Oh, I don't want to do that. I'm trying to just focus it a little bit better for you. Yeah, that's probably pretty good. So this would be cinders. So imagine these being thrown out of a volcano while it's erupting, these kind of little frothy pieces of basalt. That would be our size range for cinders. And then I'm going to need to pull the camera up a little bit to show you this last one. This is a volcanic bomb. So you can see sort of the size here relative to my hand. You can see some nice flow lines here, moving it around. It kind of tapers. This one in particular tapers at the end. So this was a piece of lava that was thrown out of the volcano airborne. Probably as it spun through the air, it developed this tapered kind of football shape look to it. Sometimes these things have actually little tails on the end of them. This did not come from this particular sample. You can see the color's a little bit off, but this is a tail of a bomb. And so they sometimes have these little tails on them, but then when it hits the ground, it's cooled enough and it's solidified enough that these tend to break off a little bit here. But this would be an example of a volcanic bomb. So just to give you some context there for those features. And then our last thing here to wrap up this episode are gases. So the other thing that is emitted from a volcano when it erupts is volcanic gases, sulfur dioxide, hydrogen sulfide, that rotten egg smell that's associated with volcanoes, but also CO2, carbon dioxide, and water vapor. Those are some other gases. And we'll talk about those as hazards later as well. But fundamentally, those are the three things that are erupted or ejected from a volcano. Lava, could be pyroclastic material and tephra, and then the gases. All volcanoes will produce gas emissions, and they might produce lava and pyroclastic material as well. In fact, I think most eruptions probably have a component of each, but in terms of the size and shape of the volcano and how we classify it, we would tend to look a little bit at what the dominant erupted material is. Is it mainly lava? Is it mainly tephra? And that helps us classify things a little bit. So hope you enjoyed this first episode number 11, an introduction to volcanoes. In the next episode, 12, we will look at volcano types and how we classify volcanoes, give you lots of examples that might be right there in your own backyard, and give you kind of a framework in which to start to identify volcanoes with some confidence. I'll also throw some quiz questions in there as well. I didn't put any in this episode, but look for some fun little quiz questions to assess your knowledge in the next episode. Thanks for your support of the channel. Appreciate it, and we'll see you next time. Take care.